what we really want to talk about is we want to talk about moving through space and time. And when I really say this, I'm really talking about what is motion mean in space-time diagrams. And there's a really surprising feature about this. And like I said, that it's like unsettling for me at least. And one of the things here is that I was giving you really two analogies here. So before I get started, I said, let's look at two analogies. The first analogy is I imagine that I have some coordinate system where it looks something like this. And I have some highway. And then I have some car that's actually driving along this highway. So you could imagine I have some car. And this is sort of like my top view of the car. And of course it has its wheels. And as this thing is moving, what we're going to imagine here is that this car is moving, let's say, 65 miles an hour down this road. So yeah, let's say that this car is a red car here, and it's moving down this road here. Now, one of the things that I said here is that sometime later, the highway changes direction. And as it changes direction, what we're really saying that it's moving now in the northeast direction. So, but what I'm going to assume here is that when I draw my car again, my car is essentially the same type of thing here, right? It's still moving at 65 miles per hour. Now, one of the things that we can actually say in this scenario here is we could say the following thing here. In the language of vectors, what we're really saying is that the magnitude is constant. But what you're really doing here is that you're taking a north vector, and now we sort of doing what? We're sort of like diverting parts along the north direction and the east direction. So I'm trying to be really careful here. So when I'm saying I'm now diverting, what do I mean by diverting? Well, what I mean here is that I'm really taking part of the velocity and I'm moving into a different dimension, right? It's not in the north dimension only, it's in the east dimension as well. So I'm really dividing my one-dimensional vector into two dimensions. And, you know, that seems fairly straightforward. But is it so straightforward? And for velocity, we're pretty comfortable, but I can also say that the same thing occurs with weight. And what I mean by weight, as I was saying last time, is that you could imagine that you're on flat floor and you're standing here on this weight scale. So when I look at this weight scale, let's say that for the sake of argument, that the weight scale here, which is of course the weight, reads 200 pounds. And we're so familiar with having constant values for weight. But weight is a vector. just like velocity is a vector, right? How do you take 65 miles, put some of it onto the north axis, some of it onto the east axis, and somehow combine it in this vector algebra, and I still get 65 miles at the end, but you're really diverting that vector into 2 dimensions. And I think weight is a little bit strange here, because you probably remember this from 4A, that if now I put this weight scale on an incline, and you're standing on the incline, well, we know that weight is truly a vector. Even though we're used to the idea that 200 pounds is just a single number, it really isn't. Because if I now, let's give it some angle like 30 degrees, what I'm really seeing here at this point here is that I'm seeing what? Well, I'm going to see an X component to the weight. I'm going to see a Y component to the weight. And if we actually measure these components, you'll find that this is about 100 pounds, and this is about 173 pounds. So even though we like to think that weight is a single number, if I put it on an incline like this, the weight is distributed both in the X and the Y. And you got to admit, it's a little bit strange. At least to me, it's a little bit strange. And so with this kind of thinking, and it's really the weight scale that really tells us that weight is not a scalar, but a vector, I now want to go through space-time. And space-time is effectively this kind of approach that we're going to see here. But now we have to make some type of leap, if I could say that. And what I'm saying here is that now special relativity forces us to make
so when I hang out with you, my
a
headphones don't work.
conceptual leap.
No, I already disconnected it from my phone.
In understanding motion through space-time. Okay? Okay, so here you go. You've taken the red pill. Let's see how you react to this little baby here. So what happens here is that I'm going to change how I'm drawing this. So I don't want to deal with space-time diagrams. It's just too confusing. I mean, it's way too confusing. And we won't move very far, like I was saying earlier. So what I want to do here is that I want to go back to sort of like Euclidean type spaces where we know what, position and time look like. So if I do that, what I want to do here is that the reason why is that if I draw a space-time diagram, versus a coordinate system like this, note that we're talking about relativity, so we have to deal with straight lines, right? There's no curvature in special relativity. So the slope of this line actually effectively means the same thing. But the problem with space-time diagrams is you have to worry about the speed of light line at 45 degrees. So in this case here, I can kind of cheat and lie and say that they're almost the same. They're not, but I want to give you a conceptual understanding, not a mathematical understanding of what's going on in space-time diagrams, because it becomes too tricky of a thing. So what I want to do then is that you're going to see that I'm going to use Euclidean plots to explain my point conceptually. Okay? I'm going to use these because they're just easier to understand. So here we go. So one of the things that I've been saying here is that space-time is the I think that's how you spell entwining. If it's not, that's okay. We'll just put quotes around that and we agree. So space-time is the entwining of both space and time. You can't separate them. And because you can't separate them, you have to move through both simultaneously. But there's a problem. The problem is that when we think about moving from one location to another, we're primarily moving through space and not so much through time. Because in our worldview, we believe in absolute time, that one observer and another observer measure the same times no matter what. But special relativity tells us that that's not the case. So what we find here is that now what we're talking about is that we will be driving through space-time now. Not Euclidean space, but space-time, which is radically different. So then if I start to think about this, what do I mean by that? Well, you could imagine that I'm going to make a series of statements. So you could imagine maybe the first thing here is that I have a stationary car. So when I think about my stationary car, I could imagine that I have a car like this, right? And as it's here, what we're really looking at here, we're looking at situations where if I plot this guy now, what I really mean is that I have a vector, and I'm going to say that this vector is these two squares right here. So in space-time, this guy is known as a space-time vector, but nobody calls it a space-time vector. What they call it, by definition, is they call it a 4-vector. Why a 4-vector? Because it has 1 time and 3 spatial dimensions. And this 4-vector is of a car at rest in space, but it's moving through time. And this is where special relativity gets really out of hand here. And so what it says here, that in space-time, the length of this vector does not change. Okay? It does not change. And I'll show you that. In fact, one of your homework problems is exactly relative to what I'm talking about right here. And so that length does not change. So what I'm going to do here is that now, what happens if the car starts moving? Okay? So now if I look at sort of like my next scenario here, so now we have a moving car. Well, just like in space-time diagrams, what you end up having is that you have some angle, you have a slope of a line. And so what I'll do here is that if I come back and I draw the same type of curve here, what you're going to see here is that, actually, I'm going to have to move this because I'm going to run out of space. So I'm going to move it down here. So what you're seeing here is that once again, I have my X and I have my time axis. But what happens here is that as this guy moves here, what you're seeing here is that the slope of this guy, if it's moving slow, is going to be the same length. So let me go draw this guy, the same length. So if these two vectors are the same length, what I want you to pay attention to here is that look at the projection of the vector onto the time axis. So if I look at the projection, what you're seeing here, look at what that means here. I have a component of time that's smaller here. So if I have a component of time that's smaller, what that really means here is that just like my example with driving from north to northeast, even though my speed is the same, part of the component goes into the north and the east in space-time, part of the component goes into time, part of the component goes into space. But the key thing here is this. Length does not change. And if it doesn't change, that means here is that, note, if I had, look at the length here. So if I look at this length here, this is 2 squares. If you look at the length here, note that this guy is what? Less than 2 squares. So what that means here is that now, relative to some frame, because I have a smaller time component, what does that mean? I have what? I have a moving clock. And what does a moving clock tells me? That it takes longer between 2 clicks, or 2 ticks, I should probably say. Right? The ticks are occurring slower relative to an observer here. So it takes longer. So what I'm saying here, since the length does not change, what you're seeing over here is that now look what I have. I now have, so if I look at this little piece right here, right, when I look at this guy, what you're seeing here is that some of the time word motion is being what? Is being diverted into space-ward motion. Some of the motion is going into the space-ward motion here. And so by taking this vector and angling it now in space-time, you're reducing the time component. And then now you have a space component that's now contributing to that. Now, it doesn't seem like such a big deal so far, but it will be here very soon. And so if I just kind of move this over here, just to be a little bit more organized here. So now what's going to happen? I'm going to move faster. So now I have a faster moving car. And if I have a faster moving car, Well, you could imagine here that I could come in and set my coordinate system as before. And if I set up my coordinate system as before, that means then when I go and I draw my vector of the same length, maybe it looks something like this here. So all of these vectors I've tried to draw with the same length here. You could see that the time component is what? This is very small time component. And then if I look at my space component, this is a very large space component. And even though I haven't really said why, I still have the same length vector. And this all really tells us about, what's really happening as far as like time dilation and stuff. But what you're finding here is that you can actually think about this car where the speed approaches c. And as you approach c, the analogy in this picture looks like this now. That component now is located where? That vector component is now along the vertical axis. Now note, I am not saying that V is equal to C. Why am I not saying that? Because if I say that, all of the laws of special relativity fail because now gamma is infinite. So what I'm really saying here is that I'm approaching this axis, but I'm not there. So I really should be saying that I'm in the limit as V is approaching C here. And if you do that, what you're seeing here is that you're seeing what? That the time component is almost zero. In fact, we would call that a little delta zero. A little tiny infinitesimal delta from that x-axis here. And this implies that the gamma factor is going towards infinity. And if the gamma factor is going towards infinity, then that means when I look at time dilation tells us what? In the limit as gamma goes to infinity, then our time dilation would then approach zero. Wait, not zero. Right? It would approach zero. And so therefore, what that effectively tells us here is that it takes an infinite amount of time between two ticks of a clock.
I would say maybe I haven't seen you use delta
And you'll see here, especially in the layman's terms, you'll hear people say, oh yeah, if an object reaches the speed of light, time stops. Well, no, because as soon as you take gamma and it goes to infinity, all of special relativity breaks down. But this is where they're saying that essentially as you get faster and faster and faster, these ticks here start to look like they'll never move. So why am I telling you this here? This analogy, remember, this is not with space-time diagrams. But this was an analogy that I gave you. this analogy precisely captures the meaning of travel through space-time. Okay? This precisely captures the meaning of traveling through space-time. So the question is, why? Well, it turns out that the structure of space-time implies that all objects move at the speed of light. All objects move at the speed of light. Now, you might be saying, well, I think that's a bunch of bullshit that Carlos is talking about. I think he's probably had one too many bourbons this morning, or whatever you want to think. I don't give a damn what you think. It's not my problem that you may be shocked by me making that statement. That's your problem. By the way, it's also my problem too. But the fact is, it's the truth. And so when a car is at rest and it's moving through space-time, right? Back here, when a car is at rest and it's moving through space-time, what's actually happening? Shit, that car is traveling through timeward motion at the speed of light. The reason why we don't see that is because we don't live in space-time. We don't have that ability to say this is intuitively what's going on. And if we start to move at some non-zero speed through space, most of that speed that we see is not through space, but it's through time. I can't separate those two together. You can't, they're entwined. Right? And as I go faster and faster, then I have more and more of my speed in space. And then that's when we say, well, that object's really booking. It's going really fast. And that's because little of that component is in time. And the homework that I'm giving you is, sort of like refers to this whole concept that I'm talking about. And what you find here is that special relativity is all about invariance. And I know I've said this a couple of times. I hate the word special relativity because I've even seen goddamn politicians saying, well, it's all relative. That's a bunch of bullshit. There are real things here. But in special relativity, the whole goal is about calculating invariance. And you're going to see in the next chapter, that's a big deal. Invariants are a big deal. Okay? So then what ends up happening is that you get the following thing. We deal with things called four vectors in space-time. And a four vector essentially tells us this thing. It means that we write x of mu, which is the common thing, and then there's a piece that's time, and then we get the x, the y, and the z here. And because these are four vectors, if we want to form scalars, so to form scalars from vectors, we use dot products. So what we do in four space is that we do 4 vector dot products. And if you write them, and I won't go into details what this means, I get this thing here that's a scalar, okay? Because it's a dot product, it's a number. Now, x squared is not an invariant for all frames of reference. Why? Different observers measure different distances. So it's not a scalar and different times. But what you find here is that when you do this dot product, you get ct squared, you get x squared, y squared, z squared. And I'm going to ignore the y and the z's, but that minus sign is correct. And what that minus sign is, it really tells us about the shape of the space where this thing lives in. It's not Euclidean space, it's Riemannian space. And what you find here is that now, if I want to take a velocity of this vector, of this 4 vector, if I want the velocity, what do I do with the velocity? Well, the velocity we typically define as what? The derivative of the position with respect to time. Now, I don't want to call this time t, because if I call it time t, it's going to mess with you when we get to the next section. Because t, we typically talk about the space-time component. So this tau here is a dummy variable. I could call it anything you want. I could call it A if you want, but it represents time. And I figured instead of using little t, I'll use a Greek tau, which kind of looks like time, but is not time in essence. So then what you do here is that this velocity now is this u of mu. So that means that this velocity has a time component and a space component. So now, what do we want? We want a scalar. So how do we get scalars? We take derivatives of them. Excuse me, we dot them. So now we want a velocity scalar, which means that I do a dot product in this Riemannian space. So if I look at this, I'm going to get, and I get this thing called u squared. Okay? Now, still, this u squared, I'm not saying that it's a scalar yet for all frames of reference. I'm just saying that it has no direction. It's a number. Now, look at what happens. Look at this form here. All 4 vectors follow the same algebra. So, what do? That means then, when I take the derivative of the velocity and I create this u squared term, that means I'm going to take the derivative with what? With respect to what? My dummy variable. So what am I taking the derivative of? Time. Because it's a component. And then this guy then forms that squared term. And then if I look at my space derivative, it looks like this here. So this is the guy that you want to look at for your problem set. Okay? So this, you could see that this is the reason why I picked tau. Could you imagine me writing little t? When this, if I had written little t, that little t and the other little t wouldn't be the same.
Carlos?
Okay? So what I'm going to do now is that I'm going to go in and I'm going to say the following thing here. If one...
Carlos, take a breath. Good Lord.
The rest frame of the observer, what you can show here is that u squared equals c squared. But wait a minute. If I get that u squared is equal to c squared, we already know that if one observer measures c in one frame of reference, this immediately implies that all observers will measure c. In other words, that's proof that objects moving through space-time, when you look at everything, always moves at the speed of light. And if you believe me, I have land in the Pacific Ocean that I want to sell you, right? It's that kind of a thing here. And you got to be going like, what is going on here, right? What is going on? So that's a really shocking feature about space-time. And you don't read that space in relativity books. Nobody tells you that. You only get that in more advanced textbooks. But it's such a deep concept. And there's a way to actually look at that.
Hey, Carlos.
This is really hard to grasp. Don't think that I'm expecting you to go like, yeah, I got it, man, baby. I understand what you're saying. You know, I'm primarily thinking about really the physics majors in some sense and just saying like, chew on this for the next 10 years and see if you grasp this shit. It's going to take a while. But I think it's super, super interesting. The mathematics clearly shows it.
Hey, Carlos,
God, is it deep.
Carlos?
So when we're talking about motion through space-time, I mean, you could see why I literally say that this is really, really bad. Okay.
Carlos, can you hear
How
us?
am I doing? You guys okay?
Oh, boy.
Okay. So I'm going to move right on.
Carlos,
Okay.
can you hear us?
So now the last thing I want to touch, which I got to finish because I want to get the hell out of this chapter, because I freaking hate this chapter because we got to deal with all this shit that doesn't really mean anything when you go to measure stuff. We want measurable stuff. So the last thing we want to do is that we want to go in and we want to talk about relativistic velocity transformations. So, hello too. So, what's going on? Am I,
You can't hear
okay,
us.
here, hold on a second. Am I muted? Can you guys hear me? Okay. They're saying that, can you hear us? No. Did I screw up on this thing?
that was the funniest thing to ever happen, Jason.
Carlos, we've been trying to get your attention for a while now.
Okay, what's
That
up?
is absolutely hilarious.
Slow down! Oh my god!
Oh, I can go back.
Yeah, that would be nice.
Oh, take a breath. Holy shit. Okay. Yeah. I think we've had a couple of questions. Let's see who's first. Manny, I think you had a question.
Maybe it's just a little bit of math semantics. You have that little red box u? You said you took a derivative in respect to tau. Did you mean a tau in the bottom there instead of a t?
Yeah, because it's a dummy variable.
Okay, because that looks like a little t instead of a big T on
Yeah,
the.
that's my question too.
No, it's because when you look at space-time intervals, right, we have this CT, but if I go to take the and we have this thing here, So now if I got to take a time derivative, right? The common thing is to say, well, I'll just take the time derivative of this thing right here, right? Right, that's what you would say, a time derivative. There's only one small problem here. These two t's are not the same thing. So I got to separate the time. And that's what I mean by a dummy variable. That time is a dummy variable. Like if I take cosine of theta, I could come in here. Oh, is that the one?
Yeah.
Oh,
That's
God
what-
damn it. Okay, thanks, Rewall. I needed that help.
That's
So
a
that
tau.
should be a tau.
Okay.
Nice, thanks.
Okay. Yeah. Yeah. Please help me. I need a lot of help all the time.
We got you, Carlos.
Yeah, we'll try. What is that? Is that a x sub mu and then x raised to the mu? Like what's?
Yes, that's exactly. I didn't want to do that, but that's how you create scalars in force space. So it really is a dot product. And maybe what I should have done is I should have done something like this. So if I have a vector r, and I dot it to another vector r, we typically write this as what? R squared? And that's exactly what I'm doing right here. But in force space.
Wait, so does
Right?
this
Because I could call Ri, where I is equal to 1, 2, 3, I could call R1 equal to X, R2 equal to Y, R3 equal to Z. And there's you may remember this from, I don't know if you do this in calculus. Have you ever done dot products where it looks like this? Ri, Rj, and you have a Kronecker delta function? Okay, sorry about that. It's too advanced here. I'll get
Not.
to it. Yeah. Yeah, it's I don't know.
does this mean that when you go to time actually slows down and you're seeing things slower than it actually is because time is being dilated? Is this thing that you're trying?
Yes, I mean that it's all embedded in this whole theory right here.
Okay.
It's all embedded in this theory.
Yeah, because that's
And when you, sorry.
Yeah,
when you say, Carlos, that this red box here is substantially our homework, is that to say that we could interpret the many or all of the problems through this lens?
No, because what we're really talking about in that one problem is talking about an invariant for the velocity. And in the other problems, we didn't talk about invariants. And this problem is the only time you're forming invariants. By the way, in the next problem set, it's almost all about invariants. So this is the only problem on the problem set that has invariant, and that talks about an invariant. Okay, getting some. Not that, so the question is that it's not about proving that C is an invariant. Maxwell's equations tells us that it's an invariant. It's the same for all inertial observers. What I'm talking about is that in order to form scalars in a space-time, you have to form dot products. And that's what this is right here. I'm forming a dot product that gives me a constant. So if it's truly a constant, then that means that if I look at this frame, or if I look at that frame, or if I look at this frame, they all measure the same speed of light. And that's what this little calculation does right here. And what you're going to find here is that this result right here is actually me writing this piece right here. There's only one more step. And then you have your answer. But you have to do what? You have to pop into the rest frame of the observer. What does the observer see in that frame? And you're going to see that it leads to this guy right here. Okay? You're going to see that it leads to that guy right there. Okay? Okay, so I'm going to move on, okay? You can always come into office hours, ask me. You could email me. There's a few of you that I have regular emails with. If it's too long of a question or if I feel like I got to write a book, I'm going to say, no, I'm not going to answer it. Come into office hours or let's set up a time and we can talk about it. That way, the words are much easier to say than to type out, you know, a couple of pages of information. Okay, I'm going to move on. Relativistic velocity transformations. I can't really say this without momentum and energy, I state without proof that the maximum speed is c. And you know, I should be really, really careful. The maximum speed that an object can have that transfers information. It's more complicated than this, but that's the easiest thing. So if somebody says that special relativity, like the way we've been dealing with up to now, says that, yeah, it says that the maximum speed is c, that's total bullshit. You need energy and momentum to actually answer that question. And so what you do here is that if we accept that is the case here, in the next chapter we'll do that, what you're going to find here is that we're going to ask the question, how do velocities transfer via a Lorentz boost? How do they transfer? And what you're going to see here is that these are very, 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 very similar to what we did with regular Lorentz transformations. So what I'm going to do here is that I'm going to have an observer from the S frame to the S prime frame. And the way we've been drawing them in the past here is we said, yeah, I got my little Earth observer right here. And then I have a rocket that's moving through space. And as it moves through space, we know that this guy here is my observer S prime and my observer S here. That's arbitrary, but we can look at it that way. And what you're finding here is that I have Lorentz transformations. Now in this case here, I'm going to do a two-dimensional transformation. I'm going to look at X and Y. Just to be really clear, we're talking two-dimensional space here. So that means then if I look at this thing, this is what we write. We know that the Lorentz transformation tells us that X prime should be gamma X minus VT. And we know Y doesn't change. It only changes if we go along the direction of motion. So if I have motion along the X, then Y does not get length contracted. And then of course I have my time here that looks like this here. So what I can do here is that I could come in here and I can look at the velocities now. Okay? And the way I look at the velocities is I take derivatives here. And as I take derivatives, I gotta be really careful here, because if I want to take the derivative for X prime, I gotta take it relative to what? T prime. So then that means here that I gotta deal with both of those primes. And so in essence, what you're seeing here is that then I'm taking the derivative of these guys right here. And if you do the algebra, this is what you get. You get a term that reads 1 minus v ux c squared, and then I get ux minus v. So what you're seeing here is that right up here, this is the old Galilean transformation or boost. The only thing that's different here is that you're seeing what? You get this denominator that pops up now. And why does it pop up? It's because you get this combination of the derivative. And it's this guy here that gives us the velocity measured from Earth as it sees this observer leave here. Now, what's really interesting about this here is that the velocity in the y direction changes now. So if you look at the position, it looks like it doesn't change, but if you look at the velocity, note that there's this x part now. Look at the denominator here. I have that x piece now. So when you look at this, I still have this time that includes x here. But then, of course, my y term only has dy. And so when you calculate this, you get the same denominator because now it's moving along that direction, but now you have this velocity in the y direction that has this limit because of this x motion thing here. And so then this gives me my primes here. And then if I look at, we're only talking about space through the space velocity. So then this gives me then what? My velocity transformations right here. Now it turns out that this becomes super important because you're going to see in the next chapter, I'm going to look at whether momentum is conserved in special relativity. And I need this y component. Now, I can do the exact same thing here. So if I go for an s prime to s, well, it's the exact same thing. One observer measures its velocities boost. The other one is going to measure the exact same, but it's going to be doing what? Moving in the opposite direction. So what do I got to do? All I do is that I replace minus sign with plus signs. And I automatically get them. one observer is not privileged to say that this is the way it is. It has to be symmetric. So that's it. That's the velocity transformation. So the question is, what does this look like? So what I want to do here is that to do that, I want to go into our next example.
Carlos, real quick, what happened to the gamma factor in the denominator of the u prime equation? So I'm just looking at your notes and I notice it's not there.
Oh, because it's actually tied into this guy right here. This is a gamma factor right here.
Oh.
Right? This is really gamma squared if you want to think about it. Because when I think about gamma, I'm getting this here, but you could see that I'm getting this 1 minus VUX. And you're seeing here that this really is my V squared term, if I could say that. It's there. And the reason why is because when you take the derivative, you'll see that you got to deal with these gammas. So what I want to do here is that you'll see here that the mathematics, again, even though they may look a little bit messier, I don't want to say they're fairly straightforward to deal with, but they're fairly straightforward to deal with. What's the hardest thing is conceptualizing what is actually happening. So I took the most convoluted problem that I could possibly imagine and then said, what does the observer see? So I want to go through this example. So the first thing that I want to do here is that let's read this and then let's start to draw pictures. It says, a particle moves with the speed 0.9 c along the x double prime axis of frame s double prime, which also moves at 0.9 c in the x positive direction relative to s prime. And then s prime is now moving relative to s at 0.9 c. So by putting all these 0.9 c's, dude, you're going like, what's 0.9 c relative to this and to that? But if you get the right picture, you'll see it's fairly straightforward. So what I want to do here is that I'm ultimately want to find the speed relative to s, but I have 3 frames of reference. So the first thing I want to tackle is the first part of the question. Okay? So what I want to do here is that I want to break this up into 3 pieces. And remember, this is all about, can you see? That's it. So here we go. So what I have here is I have a particle. What am I going to call this particle? I'm going to call it a rocket. So the rocket moves 0.9 c along x double prime axis. What do I mean by that? So I have a coordinate system. Okay? And when I look at this coordinate system, what I'm going to do here is that I'm going to call this my what? My s double prime. What's moving along the x-axis? Well, I have a little rocket here. And this rocket is moving how fast in this frame? Well, it's moving at ux double prime 0.9 c. So what do I mean by that? I have this little blue observer, right? I have my observer standing on this axis, and what he measures 0.9 c relative to him. Okay? So now you could imagine that this observer is in some faraway galaxy. But what is the galaxy doing? it's receding from a second measurer. So now what they're saying here is that now, so this is the first part. So I would call this my first piece. So I interpreted the first piece. So now I want to go to the second piece here. So now we're saying that if you read the question again, it says that the rocket frame of reference now moves 0.9 c relative to S prime. So that means then I'm going to take a different frame now. When I look at this frame, I'm seeing the following thing. I have my S frame that's primed, and this is the x-axis right there. So that means I got a little dude right here that's observing this thing now. What does he observe? Well, we're moving along the x-axis, and what you're seeing here is that when I look at my blue axis, what am I actually seeing? Well, that axis is now moving. What do I mean it's moving? Well, it's moving with a relative velocity of v equal to 0.9 c here. But wait a minute. Inside the blue frame, I have what? I have my rocket here. And this guy in this frame is moving 0.9 c here. So when I look at my frame, what I'm really seeing here is that if I look at this thing classically, if I'm in a frame moving that's 0.9 and I'm moving 0.9 within that frame, you would then say that the speed should then be 1.8 c. But what happens? That's not true, because that would violate momentum and energy, right? That's the one where I'm just saying that that's not true. What does special relativity say here? Special relativity says, who measures 0.9 c for the rocket? Right? Who measures that? The blue observer. So, who measures 0.9 c for rocket? Right? The little blue dude in S double prime. So now I'm asking the question, what does S prime C? Well, that means I got to do a Lorentz boost. What does the Lorentz boost mean? I got to go from the double prime to the prime. Okay? So then when I look at this thing, look back at the velocity transformations. If you look at the velocity transformations, if I'm going from the prime to the unprime, I got to deal with the plus signs. Because relative to him, what is that green dude doing? It's moving the opposite direction. So this means here, I use velocity boosts with positive signs. So here I go. So if I do that, then I'm going, okay, what does that observer see in the x direction? Well, it should be 1 minus VUX c squared double prime divided into double prime minus the relative velocity here. But because they're moving in the opposite direction, I got to count that. So I got to come in by hand, and I'm going to put a plus sign. because it's moving in the opposite direction. So all of the velocities now are going to be what? V is equal to 0.9 c, ux double prime is equal to 0.9 c. If you plug in these values, you'll see here that I'll have units of c. What you end up getting is that I get 0.9945 c for this. And what's important here? This guy is what? Less than c. Okay, less than c. So remember how I wrote this thing here. Look at this guy right here. What does this picture mean? This is not the correct picture. What's the correct picture? It's this. S prime, double prime is what? The rocket is what? It's at rest. Beta is 0. And what's actually moving? The other frame. Oh, this was supposed to be blue.
I just want one quick clarification. It's the correct frame in the sense that of what we would observe, but obviously relatively in the S prime frame, the rocket's moving.
No, but when we do the boost transformation, it's the rocket that's at rest.
Okay.
But if it's the rocket that's at rest, what's really moving then? Well, it's the frame is doing what? The frame is now moving at 0.9 c. And this would be u of x double prime. But when I look at the other frame, what's the other frame doing? It's also moving at some relative velocity of 0.9 c here. So what does this observer measure? It measures this relative velocity of the rocket. Right? This is a crazy thing here when you think about it. This picture's, again, very, very in sync with the relativity picture here. So as soon as I say this here, I mean this picture right here. That's what that Lorentz boost implies. It's not the rocket that's moving. It's the other two frames that are moving. So then I'm going to go to the next piece here. The next piece then says, find the speed relative to the S frame. So what does that mean here? So if I go, so I've done the frame of the rocket relative to double prime. Now I looked at the frame of the S frame. Now I want to look at the frame of the, S prime. Now I want to look at the S frame. So now the question that we're asking here is, what does S frame measure? Well, I could keep going along the same direction. So if I come here, here's my S frame. What does that mean? I have my observer here. So this little dude is now seeing what? Well, it sees, if I just kind of piggyback off this frame here, it now has a rocket, right? It has a rocket that is moving how fast? Well, that rocket is moving in that frame. It's moving ux prime, which is what? 0.9945 c, just like we calculated. What's it in the prime frame? Well, this frame, though, has a relative velocity of 0.9 c. So in this S prime, I know what the speed is here, so this is known in this frame, which then means I need a Lorentz boost. So how am I doing my Lorentz boost? I'm going from the prime to the S. And when you do that, what does that mean? Once again, I have the exact same scenario. Who's at rest? Well, picture-wise, it looks like this. I'll try to move a little bit faster. The true picture says that it looks like this. It's the rocket that's at rest, right? This thing is not moving, it's at rest. But what is moving? Well, the S frame, the S prime frame is now moving at some X prime in the opposite direction, right? I would have my minus sign here, which is 0.9945 C here. And then in my red frame, my S frame, this guy is moving at some relative velocity of 0.9 C here. That's what that boost transformation is telling me now. So if I need to do the boost transformation, look at the minus sign. I gotta include the minus sign. So if I come in and do this thing here, what you're gonna find here is that my Lorentz transformation then looks identical as before. So I get 1 minus, not minus, but and then this guy's, oops, I wrote a double. It shouldn't be double. It should be just a single. And then I have, what is it? U of x prime plus v. And if you compute that, then I'm going to get 0.994. 0.9. Then I get the same type of thing. C, and the value that I end up getting at the end is 0.9997 C for Ux of t. So what does that rocket measure? It measures this little red observer right here. He is actually moving with some speed u of x, which is that guy right there.
So you got the negative from the observer moving away, or I just don't get like.
Yeah, but by the way, that negative, you have to go all the way back up here. When you do the calculation, that negative shows up as a positive value there and a positive value there. But you got to do the algebra and it will show you that.
Oh, okay.
Okay, I only put that negative sign here to just remind you that there's a reason why we switch from negatives to positives, because the velocity is now in the opposite direction.
Okay. Okay, perfect. Thank you.
You bet. Dude, this is the end of the chapter, dude. I'm so happy to beat the hell out of this thing.